Let's talk about questions I can ask you about eddy currents on the exam. So we haven't thoroughly learned about eddy currents yet, but all we know about eddy currents so far is that they are induced by the electromagnetic field, which is lines of flux. So here are our lines of flux, our electromagnetic field, and eddy currents are the swirling reverse currents induced on the surface of metal conductors by the changing magnetic field. So what I can ask you is, what direction would the eddy currents be forming? And the answer would be they are perpendicular to the flux lines. So here's our current is going this way. Perpendicular to that are our flux lines, and perpendicular to that are our eddy currents. I can also ask you, hey, here's a laminated material. It has a fiberboard. It has sheet steel, and then fiberboard, sheet steel, fiberboard, sheet steel. Okay. So let me give you an example of a laminated material: fiberboard, sheet steel, fiberboard, sheet steel. Where are the eddy currents going to be? Are they going to be on the fiberboard, or are they going to be on the sheet steel? So let's say, it looks like we're doing our eddy currents in red, which is a good idea because eddy currents are sad, they're bad, they are losses. Well, the eddy currents are going to be inside the sheet steel. There are no eddy currents in free space. That's why we laminate. So the fiberboard is a lamination. It has a permeability of free space, and there are no eddy currents in free space. That's why we choose to do this, because now this has pretty small eddy currents compared to a piece of steel. Say this is cast. Cast steel would have these massive eddy currents, would have so many eddy currents in there. And this would be sad. This would be too much eddy. Okay, so know the difference between those, and all you do, like all you need to know is kind of what eddy currents are and how they work. Now, I just glossed over a massive point here. In my underlining here, here's what I do in code. I ask people, I ask 60 students, and there's almost 60 students here. I ask 60 students, what's a really important word to highlight in here if you were studying? What do you think I'm going to be testing you on in here? Let's see. In the chat window, what do you think are the testable concepts? Look into my world for a minute and see what are the testable concepts here. Let's see. Any professors in the room? Ah, yes. Ivan, Braden, Pranish. Yes. Okay. Let's give a few more people time to think about this. Okay. Thank you. I like to see who's engaged. I would say that they're on the surface where they are. We already talked about that. They're already called eddy currents. I wouldn't highlight currents. I'm not going to test you and say, what are they? Are they a current? Because they're called eddy currents. You're going to remember that. But they are on the surface of metal conductors, and they are induced by a changing magnetic field. You're going to remember they're induced by magnetism. That's what this course is. But they're induced by a changing magnetic field. So really, really, really important. We'll do all the changing stuff in green, okay? On your final exam, I'm going to be testing you on this topic and on this topic. It's induced on the surface. It's perpendicular. That's that topic, okay? They're not in free space. It's a surface of metal, okay? Not in free space. So there we go. We answered those. Changing magnetic field. So this magnetic field, what do I mean by it changing? Magnetic field changing. How can a magnetic field change? Calvin says changing current. Changing current how? All right. Steve says a change in direction. Okay, Ivan, new magnetic field. Motion of charges, we're overthinking a little bit there. The amount, reversing the flux. How do we reverse the flux? Current flow, what about the current flow? Faraday experiment, yes, it is like the Faraday experiment. AC current causes fluctuations in the direction of, Braden. AC current causes fluctuation in the direction of a magnetic field and more. Prajnesh, alternating current, yes. Number of turns is a good guess, but once you make those turns, it's kind of sitting on your desk always with that number of turns. It's already in the transformer with that number of turns. We don't really change it. All right, so I had a lot of good guesses and a lot of people kind of close to it there. But yes, it does have to do with the current. And I want you to imagine what happens. Okay? This is where students get messed up on the test. Okay? So, and what I'm talking about here is high average students. This is where high average students lose their grades on the type of test that I want to write for you. Okay, ready for that? I have my high grade students right here. Okay, here's what happens. You have an AC source in here. AC. That means current goes up. Current goes up. And this is current. And current goes down. Current reaches zero, right? So then what happens to our electromagnetic field is, I want you to think about it, okay? Think about the flux lines at zero current. There are no flux lines at zero current. Think about the flux lines here, halfway to the top. Well, then some flux lines have occurred, but how did they get there? So here you go. Let's say these ones are halfway up. How did they get there? Did they just appear? I'm going to go to the chat window. What's the word for how they got there? Did they appear? Did they come out of nowhere and look exactly like this? They were induced, yes. Traveled, induced. What did they look like? Did they weren't there and then they got there? They grew. That's the answer. Calvin's answer. They grew. So let's do a few more diagrams here, okay? And I realize I'm not teaching you this whole concept yet. There's like a lot of thorough videos I'm going to show you that teach you the whole concept. I'm just telling you what I'm going to test you on. And then you'll be like, oh, that's what she was talking about. Now, let me draw this in between. Yes, Calvin, they grow and they shrink and then change direction and repeat. That's a perfect answer. Everybody look at the chat window. They grow, they shrink, they change direction and repeat. Okay? So, and honestly, this is where students with a high mark lose their grades. So that's current. Oops. I already have current. Let's draw the coil. I'm drawing this same thing, okay? I'm going to draw the coil. And here in yellow, then this field was just smaller. Okay, it was smaller. It was going in the same direction, but it was smaller. And then, so it went from nothing to flux lines being small. And then here, the flux lines were larger. And then if I were to draw it up here at the peak, let's see what that would look like. What would it look like at the peak? You know, it does change. They'd be bigger. There'd be more of them, many more of them. Huge. Okay. The electromagnetic field is bigger at the peak, but it goes in the same direction. All right. And then as you're going down here, they're going to get smaller again, but they're going the same direction. Okay. Oh, we're not talking about the eddies yet. Okay. So this grows. Flux doesn't just appear out of nowhere like it seems like for this course. And then flux shrinks. Okay? Flux grows there and flux shrinks there. Okay, now this is AC current. And we know that AC current means that now it goes negative. So it goes negative. And I can draw this whole part of the phase for an AC current. So now flux is actually zero. There's no flux here. No flux. No magnetic flux is going to be induced when the current is zero. And now this is going to be negative. And this flux, will it grow or will it shrink now? Because it went to zero. Is it going to grow or is it going to shrink because it's negative? Is it going to grow or is it going to shrink? I have one answer here. It is going to grow. Does everybody else agree it's going to grow? Everyone's going to say what Calvin's saying because Calvin understands this for sure. We know that. We've confirmed that. So this will grow. Exactly. But it grows differently, doesn't it? It has the reverse direction. So if I were to draw this one, then I would have to do it like this. I would have to do it, let's see, I'm going to use this blue. I'm going to put a dot here now. And I'm going to say it's this one. And what I would have to do then is I would have to remove this direction. And I would take this little bit of eddy current or this little bit of electromagnetic field and I would change its direction. Yes, I would change its direction. And then once we get to the top here, let's replace this one. I'm going to erase this. And I'm going to draw this one. And this is the peak of the current being in the opposite direction. So what we would have is lots and lots of flux in the opposite direction. And that's what happens to flux. So it grows. And then now over here, it's going to start shrinking again. Here we go. It starts shrinking again. Then it's going to hit zero. And then it's going to grow again. And then it's going to shrink again. And then it's going to hit zero. All right. So that's what's going to happen to our electromagnetic field. And I said that eddy currents, you know, the bad things that make heat, or good things if you have a induction stove, the eddy currents are induced by the changing magnetic field. So that's what we mean by a changing magnetic field. So, but in general, when the current is alternating current, then what we've given ourselves is a constantly changing magnetic field. So that's why I'm going to turn you to a lot of YouTube videos that are nicely animated and show this magnetic field getting big and small again, this flux, okay? And the eddy currents are going to get bigger and smaller again accordingly. All right? So then my question to you on the exam, let's do an exam question based on the English word changing magnetic field. Exam question. Does a magnetic field induced by a DC current create eddy currents? Thank you, Calvin. No. The magnetic field created by a DC current does not produce eddy currents. Another question for you. Exam question. Why are transformers a typical application where we have to worry about heat?
Dealing with a lot of current, and current brings heat.
What kind of current?
The eddy flavor.
Transformers, you said, deal with a lot of current. Transformers, what's another word for deal with? And be more specific about current. The whole class.
They increase or decrease it depending if it's a step up or step down.
And they increase or decrease what type of current? There we go. I'm
The eddy
getting it
current.
in the chat window now.
Alternating.
Yes, alternating current. So let's put in here the word alternating. Alternating current. Because that alternating current, so you're completely right. You're completely right that they deal with a lot of current, and because of all of that current, it's going to make heat. But the key word is here that transformers are stepping up or stepping down AC current, and that means it's alternating current, and that means it's following this sinusoid and it's growing a magnetic field, shrinking that magnetic field, growing the magnetic field negative, shrinking it again, and it keeps doing that. And the changing, it's the delta. It's the changing of that magnetic field that makes those eddy currents. So a transformer is a high current device. Well, it could be low as well, but that is constantly having that change in magnetic flux. All right. So if you have a good understanding of how eddy currents are induced, then you can answer anything about eddy currents and the amount of heat compared to the application. I can give you a DC solenoid, versus an AC transformer, and I can ask you to compare the heat. And you would think about eddy currents, and you would think about the current source, and then you can answer that question, right? But which one would be hotter? Because it all comes from this theory. So as long as we have a nice understanding of what was going on here in this really colorful chicken scratch diagram here, then we can answer a lot of questions that are going to come to us on the final exam.